Look up at the night sky and you'll see countless stars, distant galaxies, and the vast, silent darkness stretching endlessly in every direction. But here's something that might stop you in your tracks no matter where you look. The universe looks almost exactly the same. The same patterns, the same structures, the same eerie symmetry, as if the cosmos were painted with one giant brushstroke. How could something so unimaginably vast, born from chaos, be so uniform? This isn't just a passing curiosity, it's one of the deepest mysteries in modern physics. And the key to unraveling it lies in the oldest light in existence, the cosmic microwave background, or CMB. This faint glow, a relic from the universe's infancy just 380,000 years after the Big Bang, is more than just ancient radiation. It's a cosmic snapshot, a frozen moment in time that holds the secrets of how everything we know, stars, galaxies, even the very fabric of space, came to be. But the closer we look, the stranger it gets. Hidden in this primordial light are 25 baffling puzzles, clues that challenge our understanding of reality itself. Some hints suggest the universe might be far weirder than we ever imagined, filled with invisible forces, hidden dimensions, or even echoes of a time before the Big Bang. So what are these mysteries and why do they matter? Think of the CMB as the universe's first love letter, a message carved in light that's traveled across billions of years to reach us. Decoding it could rewrite our place in the cosmos, answering questions we've asked since the dawn of humanity. Where did we come from? What's really out there? And are we alone? From inexplicable cold spots to anomalies that defy physics, each enigma pulls us deeper into a story far grander than anything we've conceived. This isn't just about science, it's about adventure, about peering into the unknown and discovering what the universe has been hiding all along. So let's dive in, because the secrets of the cosmic microwave background are waiting, and they're more astonishing than you could possibly imagine. One of the most puzzling features of the cosmic microwave background is its eerie uniformity. No matter which direction we look, whether toward the edge of our observable universe or the opposite side, the temperature of this ancient light is almost identical, a steady 2.725 Kelvin. At first glance, that doesn't sound strange, but when you realize how vast those distances are and how early in cosmic history this light was emitted, it becomes a paradox. Think of it this way. If you pour hot water into two cups at opposite ends of a room, they'll eventually cool to the same temperature because heat can travel between them. But in the early universe, the regions that emitted the CMB were so far apart that light, let alone heat, couldn't have crossed the distance in time. You'd expect one patch of the sky to be blisteringly hot and another freezing cold, simply because they never had a chance to balance out. And yet they're identical to within one part in 100,000. It's like walking into a library where every book, despite being written by authors who never met, has the exact same words on every page. This is called the horizon problem, and it's one of cosmology's biggest head-scratchers. The leading solution, cosmic inflation. The idea is that an unimaginably tiny region of space, smaller than a proton, underwent a sudden, explosive expansion stretching faster than the speed of light in the first fraction of a second after the Big Bang. This would have smoothed out all irregularities, leaving behind the uniform canvas we see in the CMB. It's an elegant fix, but not everyone's convinced. Some scientists argue inflation feels too convenient, a patch for a problem we don't fully understand. Others point out that while inflation predicts uniformity, it doesn't explain why we don't see even slight variations that should have survived. And then there's the question of what triggered inflation in the first place. Was it a quantum fluctuation, a hidden field of energy, or something even stranger? The horizon problem isn't just about temperature, it's a doorway to deeper mysteries, forcing us to ask whether our universe's smoothness is a clue to forces we've yet to imagine. If the eerie uniformity of the cosmic microwave background wasn't strange enough, wait until you hear about the cold spot. Buried in this ancient light is a region so bizarre, so unexpectedly frigid, that it defies everything we know about how the universe should behave. Picture a patch of sky spanning 1.8 billion light-years, a cosmic void so vast it could swallow thousands of galaxies, where the temperature dips just a fraction lower than everywhere else. At first glance, that might sound trivial, but in a universe governed by the laws of probability, this isn't just a statistical fluke. It's like rolling a die a million times and always getting the same number. The odds astronomically low, so what could explain such a cosmic anomaly? One theory suggests this cold spot might be the scar of a cosmic texture defect, a tear in the fabric of spacetime itself. Think of the universe as a stretched bedsheet, smooth and even. But if you twist it just right, the fabric can knot, creating a flaw in the smoothness. These hypothetical defects, left over from the universe's earliest moments, could warp space-time enough to leave a chilly fingerprint in the CMB. The problem: we've never detected such textures, and their existence hinges on untested physics. Then there's the far wilder idea that the cold spot is evidence of a collision with another universe. Imagine our cosmos as one bubble in an endless froth of multiverses, each with its own laws of physics. If a neighboring bubble brushed against ours long ago, the energy of that impact could have left behind this cold imprint. It's a tantalizing thought, but without a way to probe beyond our own universe, it's as unverifiable as it is thrilling. Of course, skeptics argue the cold spot might just be an illusion, a trick of incomplete data or instrumental noise. Yet, even after meticulous checks, the anomaly persists stubbornly real. Whatever its origin, this cosmic oddity forces us to confront how much we still don't understand. Is it a flaw in our theories, a glimpse of new physics, or something even stranger, waiting just beyond the edge of our comprehension? The cold spot doesn't just challenge our models, it dares us to rethink the very nature of reality. Just when you thought the cosmic microwave background couldn't get any stranger, along comes something so peculiar it's been dubbed the axis of evil. No, this isn't the title of a sci-fi thriller. It's a genuine cosmic mystery that threatens to upend one of astronomy's most fundamental assumptions, the cosmological principle. This principle states that the universe on large scales should look the same in every direction with no special place or privileged viewpoint, but the CMB seems to disagree. When scientists mapped the subtle temperature fluctuations in this ancient light, they noticed something unsettling. These tiny variations aren't entirely random. They appear to align in a way that eerily correlates with the plane of our solar system. It's as if the universe has a hidden, preferred axis, and by some bizarre coincidence, Earth sits roughly along it. The odds of this happening by chance: about 1 in 1,000, far too low to dismiss as mere luck. Imagine tossing a handful of confetti into the air, only to watch every piece land in perfect alignment with your kitchen tiles. That's the level of weirdness we're dealing with. So what's going on? One possibility is that we're seeing the fingerprints of an unseen force or structure beyond our current understanding. Could there be some vast, invisible feature of spacetime, a cosmic filament, a gravitational wave left over from the Big Bang, or even the imprint of a universe before ours that's tugging on the CMB in this peculiar way? Some theorists have even floated the idea that this alignment hints at an asymmetry in the very fabric of the cosmos, a fundamental lopsidedness we've yet to account for. Then there's the uncomfortable alternative that this is all just a colossal observational mirage. Maybe our measurements are tainted by some subtle bias we haven't accounted for: dust in our galaxy, an error in data processing, or even the way our telescopes are calibrated. But despite years of scrutiny, the axis of evil refuses to vanish. It lingers, taunting scientists with the possibility that our universe isn't as uniform as we thought. If this alignment is real, the implications are staggering. It could mean that the universe has a north, a directionality that breaks the sacred rule of cosmological democracy. Worse yet, it might suggest that Earth occupies a disturbingly special place in the grand scheme, a throwback to the pre-Copernican idea that we're at the center of everything. That's not just humbling, it's a direct challenge to centuries of scientific progress. So is the axis of evil a statistical fluke, a measurement glitch, or a clue to something profound? For now, it remains one of the most tantalizing and controversial enigmas hidden in the cosmic microwave background. And whether it's a cosmic conspiracy or a call to rewrite physics, one thing's certain: the universe still has plenty of surprises up its sleeve. But what if the cosmic microwave background isn't just hiding anomalies? What if it's missing something? One of the most perplexing gaps in our understanding isn't what we see in the CMB, but what we don't. According to our best model of the universe, called lambda CDM, the vast scales of the cosmos should be peppered with larger temperature variations in the ancient light. These fluctuations, like cosmic fingerprints, are the seeds of galaxy clusters and the voids between them. Yet when we study the CMB at its broadest scales, these expected wrinkles are suspiciously smooth, as if someone took an iron to the fabric of the early universe. This missing structure is most glaring in what's called the quadrupole moment, a measure of how temperatures vary across the sky at the largest angles. Think of it like the bass notes in a symphony, the deep, low-frequency hum that should underpin everything. But in the CMB, that bass is oddly muted. The variations we do detect are far weaker than lambda CDM predicts, leaving cosmologists scratching their heads. It's like expecting a roaring bonfire and finding barely a flicker. So what could explain this cosmic silence? One radical idea is that the universe isn't infinite after all, that it's finite but wrapped around itself in some bizarre topology. Picture the cosmos as a hall of mirrors where space loops back on itself before reaching the scales we'd expect for those large fluctuations. If light has been traveling in circles since the Big Bang, it could smear out the temperature differences, leaving the CMB smoother than anticipated. The catch: a finite universe would require rewriting some of our most fundamental assumptions about reality. Others argue the answer lies in the quirks of inflation, that brief, violent expansion in the universe's first moments. Maybe inflation didn't just stretch space, maybe it stretched certain wavelengths of primordial fluctuations out of existence, effectively erasing the largest patterns from the cosmic record. Or perhaps we're simply seeing a statistical fluke, a rare but not impossible quiet patch in an otherwise chaotic cosmos. But here's the twist: even if the missing fluctuations are a cosmic coincidence, their absence forces us to confront how much we still don't know about the universe's architecture. Lambda CDM has been wildly successful at explaining everything from galaxy formation to the accelerating expansion of space, yet this discrepancy lingers like a stubborn crack in a masterpiece. Whether it points to a finite universe, a flaw in inflation, or something entirely unexpected, one thing's clear: the CMB's silence speaks volumes, and until we solve this puzzle, our map of the cosmos remains frustratingly incomplete. Now let's talk about something that sounds like it's straight out of a cosmic horror story: the dark flow. Imagine the entire observable universe as a vast ocean, with galaxies and clusters drifting along like ships on gentle currents. According to the laws of physics, these motions should be random, like leaves scattering in the wind. But something's off. When scientists studied the movements of hundreds of galaxy clusters, they noticed something spine-chilling: a strange, coordinated drift in one direction, as if some unseen hand were tugging them toward a point beyond the edge of everything we can see. This eerie phenomenon wasn't guessed at, it was measured. Using distortions in the cosmic microwave background, astronomers detected a subtle but unmistakable Doppler shift, a telltale sign that these clusters are all moving together at breakneck speeds, some clocking in at nearly 2 million miles per hour. The kicker, the direction of this motion points toward a region of space with no known superclusters, no massive attractors, nothing that should be pulling everything in the universe like a cosmic magnet. It's as if the universe itself is being dragged toward something we can't see, something beyond our cosmic horizon. So what could possibly explain this? One possibility is that the dark flow is real evidence of gravitational influence from structures outside our observable universe. Picture a fish in a pond, unaware of the world beyond its waters. If someone tossed a rock into the pond nearby, the ripples would tug the fish in a certain direction. Could the dark flow be our first glimpse of ripples from a rock we can't see, an entire other universe, or a massive concentration of matter lurking in the unfathomable darkness beyond? The implications are staggering. It would mean our cosmos isn't just one lonely island of existence, but part of something vastly larger, connected in ways we're only beginning to suspect. But not everyone's convinced. Skeptics argue the dark flow could be a quirk of our measurements, a mirage caused by incomplete data or subtle errors in how we interpret the CMB. After all, catching the motion of galaxy clusters across billions of light years isn't like tracking cars on a highway. Tiny inaccuracies could snowball into illusions of grandeur. Some researchers have even suggested that peculiarities in the way our solar system moves through the CMB could be skewing the results, making it seem like the entire universe is flowing when it's just our own backyard playing tricks on us. Yet after years of debate, the dark flow refuses to disappear. Newer studies using deeper and more precise data continue to find evidence of this mysterious motion. And if it's real, it doesn't just hint at unseen neighbors, it challenges one of cosmology's bedrock assumptions, that the universe on the largest scales should be uniform and isotropic. If the dark flow is truly a cosmic current pulling us toward the unknown, then everything we thought we knew about the limits of our universe might just be the tip of the iceberg. Whether it's a groundbreaking discovery or a ghost in the data, one thing's certain: the dark flow forces us to confront how little we understand about the vast, dark ocean of space beyond our tiny island of light. And that's the kind of mystery that keeps astronomers awake at night, staring into the void, wondering what's out there, pulling us toward the unseen. The cosmic microwave background doesn't just hold secrets about the universe's structure, it also carries clues to one of the most frustrating mismatches in cosmic chemistry. According to the pristine calculations of Big Bang nucleosynthesis, the early universe should have cooked up precise amounts of lightweight elements like hydrogen, helium, and lithium. And for the most part, those predictions line up beautifully with what we see except for lithium. There's a glaring shortfall, and it's baffled scientists for decades. Here's the problem: when we peer into some of the oldest stars in the galaxy, relics from nearly 13 billion years ago, their lithium levels are 3 to 4 times lower than they should be. These ancient stars are like cosmic time capsules, preserving the chemical makeup of the early universe, but instead of confirming our models, they're throwing us a curveball. It's as if you followed a recipe perfectly, only to open the oven and find half the ingredients missing. So where did the lithium go? One possibility is that our understanding of stellar physics is incomplete. Maybe these primordial stars destroyed lithium over time, swallowing it up in nuclear reactions we haven't fully mapped. Some theories suggest turbulent mixing in stellar interiors could have dragged lithium down into hotter layers where it fused into heavier elements and vanished. Others propose that cosmic rays slamming into interstellar material might have broken apart lithium nuclei before they could settle into stars, but the more thrilling and radical solution points to gaps in our particle physics. What if unknown particles floating through the early universe interfered with nuclear reactions during those first crucial minutes? Certain exotic candidates, like hypothetical dark matter particles, could have absorbed neutrons or altered reaction rates, throwing off the delicate balance of element production. It's a long shot, but if true, it would mean the lithium problem isn't just about stars, it's a whisper from the dark sector of the universe, hinting at physics beyond the standard model. Then there's the wild card. What if our measurements are wrong? Some astronomers argue that ancient stars might hide lithium in their outer layers, masking its true abundance. Or perhaps the primordial plasma wasn't as uniform as we thought, creating pockets where lithium formed differently. But despite decades of hunting, no one's found a smoking gun. The lithium problem is more than a cosmic accounting error. It's a tug of war between theory and observation, forcing us to question whether we've missed something fundamental about the universe's first moments. Solve it, and we might unlock secrets about everything from stellar evolution to the nature of dark matter. Until then, it remains a quiet but persistent reminder that even our best models are still works in progress. Among the most urgent puzzles in modern cosmology is the Hubble tension, a disagreement so stubborn it's been called a crisis. Here's the heart of it. When we measure how fast the universe is expanding today using nearby galaxies and supernova, we get one number. But when we calculate that same expansion rate by studying the cosmic microwave background, we get a different, noticeably smaller value. These aren't tiny discrepancies lost in the margins of error. The gap is significant, nearly 10%, and it's persisted despite decades of increasingly precise measurements. It's as if two clocks, both impeccably built, kept ticking at different speeds for reasons no one could explain. The local measurements, relying on Cepheid variable stars and Type 1a supernova as cosmic yardsticks, consistently peg the Hubble constant at roughly 73 kilometers per second per megaparsec. Meanwhile, the CMB-derived value, extrapolated from the universe's baby pictures using lambda CDM, lands closer to 67. At first glance, that might not sound like much. But in the precise world of cosmology, where even a 1% deviation can upend theories, this split is seismic. It suggests something fundamental is missing from our understanding of cosmic evolution. So what could bridge the gap? One leading contender is early dark energy, a hypothetical form of energy that might have briefly surged during the universe's first few 100,000 years, subtly altering how fast space stretched during those critical early moments. Imagine blowing up a balloon in short, uneven bursts instead of a steady exhale. The final size might look the same, but the path to get there leaves hidden fingerprints. Early dark energy could have tweaked the CMB's apparent expansion rate without leaving obvious traces elsewhere, explaining why today's measurements don't align. Others speculate the tension points to flaws in lambda CDM itself. Maybe dark matter isn't as simple as we've assumed, or perhaps gravity behaves differently on cosmic scales than Einstein's equations predict. There's even a fringe idea that our universe collided with another bubble of spacetime long ago, injecting extra energy that skewed local expansion rates. But skeptics aren't ready to rewrite physics just yet. Some argue the discrepancy stems from overlooked errors in local measurements, like subtle miscalibrations in the cosmic distance ladder or unaccounted for dust obscuring supernova. Others suggest the CMB analysis might be missing key nuances, like the gravitational pull of unseen structures warping the ancient light. The stakes couldn't be higher. If the Hubble tension is real and not just a cosmic mirage, it implies that 13.8 billion years of cosmic history might need a rewrite. Whether it's early dark energy, new physics, or something even stranger, one thing's clear: the universe is handing us a mystery, and solving it could crack open the next chapter in our understanding of everything. The cosmic microwave background is often described as a near-perfect snapshot of the early universe, a uniform glow with only the faintest ripples of temperature variation. But when scientists looked closer, they stumbled upon something unsettling. The universe's baby picture isn't symmetrical. One half of the sky appears ever so slightly warmer than the other, as if the cosmos were leaning into a cosmic breeze. This bizarre imbalance, known as the dipole asymmetry, defies our expectations of how the universe should behave. At first, researchers thought it might be an illusion, an artifact of our own motion through space. After all, Earth orbits the Sun moves around the galaxy, and the galaxy itself hurtles through the cosmos at over 1,000,000 miles per hour. This movement creates a Doppler shift in the CMB, making light from one direction appear warmer and the opposite cooler, like the sound of an ambulance rising as it approaches and fading as it speeds away. But when astronomers accounted for all known motion, something didn't add up. The asymmetry persisted, stronger than it should be, hinting at something deeper at play. One radical explanation is that the universe itself might be rotating. Imagine a cosmic whirlpool where space-time itself twists ever so slightly, dragging the CMB along with it. This spin, if real, would imprint a subtle temperature gradient across the sky, a lopsidedness that matches the dipole we observe. The problem, general relativity, suggests the universe has no preferred axis, no edge to push against to generate such rotation. And yet, the data whispers otherwise. Another possibility involves primordial magnetic fields, invisible threads of force woven into the fabric of the early universe. These fields, if strong enough, could have nudged electrons and photons in one direction during the CMB's formation, leaving behind a faint thermal bias. It's like blowing gently across a cup of hot tea, creating a warmer spot on one side. Some theories even suggest these magnetic relics could be tied to dark matter or other exotic physics, offering a bridge between the dipole and other cosmic mysteries. Then there's the unsettling chance that the asymmetry isn't cosmic at all, that it's a shadow cast by something in our own galactic backyard. Interstellar dust or gas could be filtering the CMB unevenly, creating a false dipole. But meticulous studies have largely ruled this out, leaving the anomaly frustratingly real. The dipole asymmetry isn't just a quirk, it's a challenge to our assumptions about the universe's symmetry and simplicity. If it's real and not some statistical fluke, it means the cosmos might have a hidden handedness, a gentle tilt in the grand scheme we've yet to understand. Whether it's a relic of rotation, a magnetic fossil, or something even stranger, this lopsided whisper from the early universe reminds us, the more we map the cosmos, the more it refuses to fit neatly into our models. The cold spot in the cosmic microwave background isn't just a temperature anomaly, it might be a window into one of the universe's most baffling architectural oddities, a supervoid. Picture a cosmic desert, a region of space so vast and empty it stretches nearly 2 billion light-years across, where galaxies are eerily scarce. Such voids exist elsewhere in the universe, but this one, if real, would dwarf them all. And here's where things get weird. Nestled right where the cold spot sits, astronomers have found hints of a sprawling underdensity in galaxy distribution. At first glance, it seems like a perfect match. A giant void could explain the chill in the CMB through something called the Sachs-Wolf effect. Here's how it should work. When light travels through a void, it climbs out of a gravitational well. Since gravity in these regions is weaker, photons gain a tiny bit of energy, making them appear slightly cooler when we observe them. It's like rolling a ball up a shallow hill. The effort saps its speed, leaving it just a little slower on the other side. But when researchers measured the depth of this proposed supervoid, the math didn't add up. The temperature drop in the cold spot is about 70 microkelvin, while the void's observed structure can only account for maybe 20. That leaves 50 unaccounted for, a discrepancy too large to ignore. So is the void not as empty as we thought, or could there be something else amplifying the effect? One tantalizing idea is that this supervoid isn't just a lack of galaxies, it might be threaded with an unusual distribution of dark energy or some other exotic force, warping spacetime in ways we don't fully grasp. Imagine a sponge soaked not with water, but with an invisible fluid that alters the very fabric of space. If dark energy behaves differently here, it could deepen the gravitational well, stretching the Sachs-Wolf effect beyond expectations. Then there's the possibility that we're not seeing the whole picture. Voids aren't perfect spheres, they're lumpy, irregular structures. If this one has hidden substructures, clumps of matter or tangled magnetic fields, they could be bending light in ways that exacerbate the cooling. Or perhaps the void is older than we think, a relic from a time when the universe's expansion was accelerating faster, leaving behind a colder, more pronounced imprint. But skeptics have another take. Maybe the void and the cold spot are cosmic neighbors by pure chance, their alignment a trick of perspective rather than cause and effect. After all, the universe is vast and coincidences happen. Yet the odds of two such rare features overlapping randomly are slim, leaving scientists torn between revising physics or accepting an astronomically unlucky roll of the dice. Whatever the truth, the missing supervoid mystery forces us to confront how much we still don't understand about the large-scale structure of the cosmos. Is it a flaw in our models, a sign of new physics, or just a shadow cast by something even stranger lurking in the darkness? Until we peer deeper into this cosmic emptiness, the cold spot's chill remains one of the universe's most tantalizing unsolved whispers. When we look at the cosmic microwave background, we usually picture its temperature variations as random like static on an old television set, a chaotic but predictable jumble of hot and cold spots. This assumption isn't just a guess, it's baked into nearly every model of the early universe. The math tells us these fluctuations should follow what's called a Gaussian distribution, meaning their sizes and shapes should cluster around an average with no unexpected patterns. But the universe loves breaking rules. Hidden in the CMB's subtle wrinkles are anomalies that defy this tidy statistical picture, odd, structured shapes that stand out like perfectly formed snowflakes in a blizzard. Take the so-called flying saucer pattern circular hotspots with sharp edges, looking less like random noise and more like deliberate imprints. These aren't just quirks, they're potential evidence that the early universe wasn't as uniform as we thought. Under Gaussian statistics, finding something like this should be as likely as shuffling a deck of cards and drawing a perfect royal flush 5 times in a row. So what could carve such precise patterns into the fabric of the cosmos? One explanation tugs at the very heart of inflation theory. Most models assume inflation was driven by a single quantum field, a solitary force stretching space into smoothness. But what if there were multiple fields at play? Picture 2 dancers moving in sync. Sometimes their steps align perfectly, creating harmonious patterns. Other times they clash, leaving behind traces of their interaction. In multi-field inflation, these cosmic dancers could have created resonant features in the CMB, like those flying saucer shapes through their interplay. It's a compelling idea, but it raises thorny questions. How many fields were there? How did they interact? And why haven't we seen clearer evidence of their fingerprints elsewhere? Then there's the wild card, topological defects. Imagine the early universe cooling like molten metal, and as it hardened, cracks formed in spacetime itself. These defects, cosmic strings, domain walls, or textures, could have twisted the CMB's fluctuations into non-Gaussian shapes as they moved through the primordial plasma. Think of dragging a stick through wet sand. The ripples left behind aren't random, they bear the mark of the disturbance. Some theories suggest these defects might even explain other anomalies, like the cold spot or the axis of evil, tying multiple mysteries into one grand cosmic narrative. But skeptics aren't ready to discard Gaussianity just yet. Could these odd patterns simply be flukes, the result of our limited vantage point? After all, we only have one universe to observe, and statistical anomalies might be inevitable in a cosmos this vast. Or perhaps the instruments studying the CMB introduced subtle artifacts, creating illusions of structure where none truly exist. Yet with each new observation, the case for non-Gaussianity grows stronger. If these patterns are real, they could rewrite our understanding of the universe's birth, revealing a far more dynamic and textured early cosmos than we ever imagined. Whether it's multi-field inflation, space-time defects, or something even stranger, one thing's clear: the CMB's random noise might be hiding a cosmic symphony, and we're just beginning to hear the notes. What makes the cosmic microwave background even more astonishing isn't just its age or its anomalies, it's how perfectly it mimics the radiation of an ideal blackbody. Picture a piece of iron heated until it glows red-hot. The light it emits follows a very specific curve, a fingerprint of intensity at every wavelength dictated solely by temperature. The CMB does the same thing, except its curve is the most flawless blackbody spectrum ever measured in nature, matching theoretical predictions with a precision of 1 part in 10,000. That's like baking a cake where every single molecule of sugar is exactly where it should be. But here's what's truly mind-bending: this perfection emerged from what should have been total chaos. The early universe was a seething maelstrom of plasma, a soup of particles colliding, annihilating, and screaming through space at unimaginable energies. Photons were constantly scattered, absorbed, and re-emitted in a frenzied dance, and yet, by the time this light broke free, 380,000 years after the Big Bang, it had somehow settled into this pristine thermal equilibrium. How? The secret lies in a process called thermalization. During those fiery early moments, the universe was so dense that photons couldn't travel far before slamming into an electron. Each collision redistributed energy, smoothing out irregularities until everything reached a uniform temperature. It's like shaking a bag of marbles relentlessly. Eventually, their energy evens out, no matter how violently you started. But this doesn't just explain the blackbody's perfection, it makes deviations from it all the more intriguing. Even the tiniest departure from that ideal curve could signal something revolutionary: particles decaying into photons, extra dimensions warping light, or even echoes of a pre-Big Bang universe. Imagine finding a single misaligned stitch in an otherwise flawless tapestry. That's what cosmologists are hunting for. Some theories predict that certain exotic particles, like actions or sterile neutrinos, might have subtly interacted with CMB photons, leaving faint spectral fingerprints. Others speculate that if extraspatial dimensions exist, they could have leaked energy into or out of the early universe, tweaking the blackbody curve in ways we're only beginning to model. Then there's the tantalizing possibility that the universe didn't start perfectly uniform. Quantum fluctuations during inflation could have created microscopic hotspots where photons carried a fraction more energy. If these regions survived thermalization, they might appear as spectral bumps, whispers of a more complex cosmic dawn. So far, missions like COBE, WMAP, and Planck have found no significant deviations. But the hunt isn't over. Future telescopes with even finer sensitivity could uncover anomalies hiding in the noise, and if they do, it wouldn't just refine our models, it could crack open entirely new realms of physics. The CMB's blackbody perfection isn't just a triumph of cosmology, it's a silent sentinel guarding secrets we've only begun to imagine. For nearly 400 million years after the Big Bang, the universe was cloaked in darkness, a thick, impenetrable fog of neutral hydrogen gas that swallowed starlight whole. Then something extraordinary happened. The fog lifted, space became transparent, and light could travel freely for the first time. This monumental shift, called reionization, marks one of the most pivotal yet least understood chapters in cosmic history. And buried within the polarized light of the cosmic microwave background are cryptic clues about how it unfolded. Think of the CMB's polarization as delicate brushstrokes on a canvas, revealing not just the universe's temperature fluctuations but also the direction of ancient light waves. When the first stars and galaxies ignited, their ultraviolet radiation ripped electrons from hydrogen atoms, ionizing the gas and clearing the cosmic haze. This process should have left a specific imprint on the CMB's polarized patterns, like fingerprints on glass. But when scientists compared these imprints to predictions, the numbers didn't quite add up. The timeline was off. The energy required seemed greater than what early galaxies alone could have produced. It's as if we'd found a city powered by a single candle, with no explanation for where the extra light came from. So what else could have driven reionization? One leading suspect is quasars, supermassive black holes at the hearts of young galaxies, devouring matter and spearing the darkness with jets of intense radiation. These cosmic lighthouses are undeniably powerful, but here's the catch: they're also rare. Current observations suggest there simply weren't enough quasars in the early universe to ionize all that hydrogen alone. It's like trying to thaw a frozen lake with a handful of matches. The math leaves a glaring energy deficit, forcing astronomers to ask, were there hidden players in this cosmic dawn? Enter dark matter, not the sluggish, cold dark matter we know today, but an exotic variant particles that might have decayed or collided, releasing bursts of energy that helped strip electrons from hydrogen. Imagine a shadowy workforce laboring behind the scenes, their contributions invisible but essential. Some theories even propose that these dark matter interactions could have produced dark stars, objects fueled not by nuclear fusion but by the annihilation of dark particles glowing faintly in the primordial gloom. If such stars existed, their death throes might have seeded the universe with just enough extra radiation to tip the scales, yet not everyone's convinced. Critics argue that we might be underestimating the ultraviolet output of early galaxies, their starlight amplified by factors we haven't accounted for, like rampant star formation or unexpected stellar properties. Others suggest that reionization wasn't a uniform process but a patchwork, with ionized bubbles forming and merging at different rates, leaving a messier but still plausible trail in the CMB. The truth is, we're still piecing together this cosmic whodunit. Future telescopes like the James Webb Space Telescope could spot fainter, earlier galaxies or rule them out as the sole culprits. Meanwhile, subtle anomalies in the CMB's polarization might yet betray dark matter's role, offering whispers of physics beyond our current grasp. One thing's certain: the reionization riddle isn't just about light piercing darkness. It's a detective story spanning billions of years, where every clue rewrites our understanding of how the universe woke up. Among the faint echoes of the cosmic microwave background lies a shadowy imprint of one of the universe's most elusive particles, the neutrino. These ghostly particles, trillions of which pass through your body every second without a trace, barely interact with matter, yet their collective gravity has subtly warped the CMB in ways we're only beginning to decode. The patterns in this ancient light don't just tell us about photons from the dawn of time. They hold clues to the mass of neutrinos, a property so vanishingly small that it defied measurement for decades. Here's the catch: when cosmologists calculate neutrino masses using the CMB's large-scale structure, the numbers don't quite align with results from particle physics experiments on Earth. It's as if the cosmos and the lab are whispering two slightly different stories. Take the so-called neutrino anomaly, a stubborn discrepancy where lab-based observations, like those from the mini-Buani experiment, suggest neutrinos might oscillate between flavors in ways that don't fit the standard model. Some theorists argue this could point to the existence of sterile neutrinos, a hypothetical fourth flavor that interacts only through gravity, leaving no footprint in detectors except a gravitational tug on the fabric of spacetime. But the CMB complicates the picture by analyzing how neutrino gravity influenced the growth of cosmic structures. Planck satellite data placed an upper limit on the combined mass of all three known neutrino flavors, roughly 0.12 electron volts, or about a millionth the mass of an electron. That's staggeringly light, so light that it raises eyebrows. If sterile neutrinos exist, their extra mass should have left a detectable warp in the CMB's clustering patterns. Yet so far, no such signal has emerged. The universe seems to be holding back, teasing us with contradictions. Could the answer lie in the way neutrinos shaped the universe's toddler years? In the chaotic era just after the Big Bang, neutrinos raced outward at near light speed, their sheer speed preventing them from clumping together like dark matter did. This created a drag effect on the formation of galaxy clusters, a subtle smoothing visible in the CMB's texture. But if sterile neutrinos were part of that mix, slower, heavier, and more prone to clustering, their absence in the data is either a fatal blow to the theory or a sign we're missing something deeper. Or perhaps the anomaly isn't in the neutrinos at all. What if our models of the early universe are incomplete? Some researchers propose that unknown forces, early dark energy, modified gravity, or even primordial magnetic fields could mimic the gravitational effects of light neutrinos, tricking our measurements. Others wonder if the CMB's constraints are being subtly skewed by the Hubble tension or other unresolved cosmic inconsistencies. One thing's certain, the neutrino shadow in the CMB isn't just a puzzle about mass. It's a tug of war between the infinitely large and the infinitesimally small, where cosmology and particle physics collide. Solve it, and we might not just crack the mystery of sterile neutrinos. We could uncover a hidden layer of reality, one where the faintest particles hold the keys to the universe's grandest structures. Until then, the ghostly whisper of neutrinos remains just out of reach, taunting us with questions written in the oldest light there is. One of the most profound revelations from studying the cosmic microwave background is the apparent flatness of our universe. The angles of temperature fluctuations in the CMB align almost perfectly with what you'd expect if space had zero curvature, no overarching bend, no global warp. This flatness, backed by Planck satellite measurements with razor-thin margins of error, has become a cornerstone of modern cosmology. But here's the twist: flat doesn't necessarily mean infinite. Our universe could still be finite, even bizarrely shaped like a cosmic donut without betraying its secret in the CMB's light. At first glance, the data seems unambiguous. When cosmologists measure the density parameter of the universe, denoted by the Greek letter omega, it lands tantalizingly close to 1, the magic number for perfect flatness. A value greater than 1 would imply a closed, spherical universe where parallel lines eventually converge. Less than 1, and space would be open, hyperbolic, like an infinite saddle. Yet our measurements cling to 1 with uncanny precision, as if the universe had been fine-tuned to balance on this knife edge. But flatness doesn't preclude exotic topology. Imagine a video game where your character walks off the right edge of the screen only to reappear on the left. In a similar way, the universe could be multiply connected, a flat but finite space where light wraps around, creating ghostly duplicates of distant structures. A donut shape or torus is one such possibility. If our cosmos were sculpted this way, the largest temperature fluctuations in the CMB might repeat in matching pairs, like reflections in a hall of mirrors. So why haven't we spotted these echoes? The answer lies in scale. If the universe's hypothetical loops are larger than the observable horizon, their fingerprints would be too faint to detect, leaving the CMB looking flat and infinite even if it's neither. Some theorists argue that hints of these loops might still lurk in subtle correlations between distant hot and cold spots, patterns too vast for current telescopes to resolve but potentially within reach of future missions. Then there's the elephant in the room: inflation. The theory that stretched the infant universe to smoothness also predicts near-perfect flatness as a side effect. But what if inflation didn't happen, or didn't happen the way we think? Alternative models like cyclic universes or bouncing cosmologies could produce flatness through entirely different mechanisms, leaving behind topological quirks that standard inflation would erase. The real enigma is that flatness feels too perfect, like a pencil balanced on its tip, the universe's omega so precisely equaling 1 begs for an explanation. Is it sheer luck, or does it point to deeper physics, a multiverse where countless bubble universes inflate with random curvatures, and we just happen to live in the rare flat one? Until we peer deeper into the CMB's largest scales or uncover definitive repeats in galaxy surveys, the curvature controversy remains unresolved. Whether our universe is an infinite plane, a finite donut, or something even stranger, its true shape might still be hiding in plain sight, written in light, waiting for us to decipher its final geometry. Buried within the delicate ripples of the cosmic microwave background is a fingerprint, not just of the universe's birth, but of its most enigmatic resident, dark matter. When scientists mapped the CMB's acoustic oscillations, those faint, frozen sound waves from the early cosmos, they found something unexpected. The peaks and troughs of these waves didn't match predictions based on visible matter alone. Instead, they revealed the gravitational tug of something invisible, a shadowy scaffolding woven into the fabric of space itself. This was our first direct evidence that dark matter isn't just a placeholder for missing mass, it's a real, dynamic force that shaped the universe from its very first moments. Think of the early universe as a vast, primordial drum. As ordinary matter, protons, electrons, photons vibrated in the dense plasma, dark matter's gravity acted like an invisible hand, subtly damping some waves while amplifying others. The result, a distinct pattern in the CMB's temperature fluctuations, a cosmic echo that only makes sense if dark matter outnumbers ordinary stuff by 5 to 1. It's like listening to a symphony and realizing half the instruments are playing in a frequency we can't hear, yet their presence bends every note we can. But here's the frustrating twist. While the CMB tells us dark matter exists, it doesn't tell us what it is. All we know is that it must be cold, slow-moving enough to clump into the gravitational wells that seeded galaxies, and that it barely interacts with light or ordinary matter. For decades, physicists have hunted for its identity, building experiments deep underground to shield them from cosmic noise. Take Lux Zeppelin, the most sensitive dark matter detector yet, nestled in a former gold mine beneath a mile of rock. It's designed to catch the rare collision between a dark matter particle and a xenon atom, a whisper of an impact that could crack the case. But so far, after years of searching, the detector's silence is deafening. No confirmed hits, no telltale flashes in the dark. This null result isn't just a setback, it's a cosmic riddle. If dark matter is made of weakly interacting massive particles, the long-favored candidate, why haven't we found them? Could they be lighter, fuzzier, or stranger than we imagined? Some theories now point to actions, hypothetical particles so lightweight they behave more like waves than individual entities. Others suggest dark matter might be part of a hidden sector with its own forces and particles that barely touch ours except through gravity. There's even the radical idea that dark matter doesn't consist of particles at all, but primordial black holes forged in the Big Bang's fury. The CMB's acoustic oscillations hand us a paradox. They confirm dark matter's role in shaping the cosmos while stubbornly withholding its true nature. Every failed lab experiment, every null result, forces us to broaden the search, to consider possibilities we once dismissed as outlandish. Maybe dark matter isn't one thing but many, a cosmic zoo of invisible constituents, each leaving its own faint mark on the universe's oldest light. Or perhaps we're missing something fundamental, a flaw in how we interpret gravity itself. One thing's certain, the CMB has given us the map, but the treasure hunt is far from over. With every new experiment, every deeper dive into the cosmos microwave whisper, we're not just chasing a particle. We're chasing the answer to why the universe looks the way it does and what else might be hiding in the dark. Hidden within the polarized light of the cosmic microwave background are ghostly spirals, patterns so subtle they're almost invisible, yet they might hold the key to one of the universe's most dramatic upheavals. These swirling imprints, called B-mode polarization, are the cosmic equivalent of tire tracks in the snow, betraying the passage of something extraordinary. But what left these marks? The leading suspects are cosmic strings, hypothetical defects in spacetime itself, forged during the universe's earliest phase transitions. Picture the cosmos cooling from a frenzy of energy, like molten steel hardening into a blade. As it settled, cracks might have formed in the fabric of reality, one-dimensional scars thinner than a proton but stretching across billions of light years, vibrating with unimaginable tension. When these strings move, they don't just wiggle, they slice through space-time, sending out gravitational shockwaves that twist the CMB's polarization into those telltale spirals. It's as if someone dragged a stick through a quiet pond, sending ripples curling outward in delicate arcs. But here's where the mystery deepens: inflationary gravitational waves, the tremors from the universe's exponential growth spurt, can produce nearly identical B-mode patterns. Telling these two apart is like distinguishing identical twins by their shadow, a task so delicate it pushes our telescopes to their limits. The difference lies in the details. Inflationary B-modes should blanket the sky evenly, a uniform whisper from the universe's first moment. Cosmic strings, though, would leave a patchwork of twists sharper, more localized, like graffiti tags sprayed across the cosmos. Some theorists argue that recent faint detections of B-modes, like those from the South Pole telescope, hint at this very signature. Others counter that noise from interstellar dust could mimic the effect, muddying the waters. Then there's the wild card: what if both are real? Imagine cosmic strings vibrating alongside inflationary echoes, their signals overlapping like voices in a choir. Untangling them would require next-generation observatories like the upcoming Light-Bird satellite, with sensitivity so sharp they could hear the universe's faintest whispers. The stakes couldn't be higher. Confirm cosmic strings, and you found evidence of a phase transition more violent than anything in particle colliders. Rule them out, and inflation's triumph grows stronger. For now, the phantom vortices remain just that, ghosts in the data, teasing us with the possibility that space-time itself might be frayed at the edges. Whether they're relics of cosmic cracks or echoes of inflation's birth pangs, one thing's certain: the universe left us a puzzle written in polarized light, and we're only beginning to decipher its twisted line. The cosmic microwave background is often described as a postcard from the universe's infancy, but what if it carries messages from even earlier? Some daring theories suggest the CMB might contain whispers of a time before time, subtle imprints of events that occurred before the Big Bang. At first glance, the idea seems nonsensical. How could anything precede the very birth of space-time? Yet cutting-edge physics paints a startling picture. Our universe might not be the first or the last in an endless cycle of cosmic rebirth. Take loop quantum gravity, a radical framework where space-time isn't smooth and continuous but woven from tiny, indivisible threads. Here, the Big Bang wasn't a true beginning but a bounce, a moment when a previous universe collapsed under its own gravity, squeezed into an unfathomably dense knot, then exploded outward anew. This rebound would have left faint scars in the CMB's temperature patterns, subtle asymmetries or concentric ripples, like echoes bouncing between cosmic walls. While no smoking gun has been found yet, some researchers argue that anomalies like the cold spot or the axis of evil could be remnants of that primordial crunch, wrinkles in spacetime's fabric that survived the transition. Then there's Roger Penrose's conformal cyclic cosmology, an even more mind-bending vision where universes endlessly die and are reborn through a process called conformal rescaling. In this model, the distant future of one universe where all matter has evaporated into radiation and black holes have decayed becomes mathematically identical to the ultra-smooth, ultra-hot dawn of another. The boundary between cycles vanishes and information from the old universe leaks into the new one. Penrose claims to have found evidence of this in the CMB, circular patterns of temperature variation he calls Hawking points, theorized to be the last gasps of supermassive black holes from a prior eon. Not everyone's convinced. Critics argue these patterns could be statistical flukes or artifacts of data processing. The real puzzle is that if the universe truly cycled through countless iterations, why wouldn't entropy, the inevitable march toward disorder, pile up with each bounce, leaving each new universe messier than the last? Some theorists counter with wild solutions like quantum resets that purge entropy at each transition, or hidden dimensions where disorder bleeds away unnoticed. The audacious idea of a pre-Big Bang universe forces us to confront the limits of our cosmic archaeology. If these theories are right, the CMB isn't just a relic of creation, it's a palimpsest layered with echoes of universes we can scarcely imagine. Future experiments hunting for gravitational waves from the Big Bang's first instance might settle the debate, catching ripples that betray whether our cosmos was born in fire or inherited from ashes. Until then, the CMB's quiet glow keeps its oldest secrets close, daring us to read between the lines of time itself. The cosmic microwave background's mysteries only grow stranger the deeper we look, and one of the most perplexing twists comes in the form of the octopole moment, an 8-lobe pattern that refuses to behave randomly. When scientists mapped the CMB's temperature fluctuations at this scale, they found something unsettling. The octopole isn't just doing its own thing. It's eerily aligned with the quadrupole, the 4-lobed pattern we discussed earlier, as if some invisible hand had arranged them in cosmic lockstep. Statistically, this shouldn't happen. If the universe were truly random and isotropic, these patterns would point in entirely different directions, like compass needles spinning freely. Instead, they're synchronized, a coincidence so unlikely it's like shuffling 2 decks of cards and dealing out identical hands twice in a row. So what could force these patterns into alignment? One compelling idea points to primordial magnetic fields, threads of force woven into the fabric of the newborn universe. Imagine the early cosmos as a stormy ocean, with currents of magnetism swirling through the plasma. These fields, if strong enough, could have nudged photons and electrons in specific directions as the CMB formed, leaving behind a subtle bias in the temperature fluctuations. Think of it like wind etching parallel ripples into sand dunes, nature's invisible hand leaving a faint but detectable signature. The problem: we've never directly observed magnetic fields from this era, and their existence hinges on untested physics. Then there's the unsettling possibility that this alignment isn't cosmic at all. It's an artifact of how we observe the universe. Our solar system moves through the CMB at a brisk clip, creating a Doppler shift that warps our measurements. Could this motion, combined with galactic dust or instrument noise, be tricking us into seeing patterns where none exist? Some researchers argue that imperfections in data processing, like the way we subtract foreground interference, might amplify minor correlations into false signals. It's the astronomical equivalent of seeing faces in clouds. Our brains are wired to find patterns, even in chaos. But the plot thickens when you consider the quadrupole-octopole alignment isn't isolated. It's part of a broader puzzle that includes the axis of evil and other large-scale anomalies, all pointing toward a tantalizing question: is the universe subtly lopsided? If these alignments are real, they could hint at a fundamental asymmetry in the cosmos, a preferred direction baked into space-time itself. Some theories even suggest this might be a relic of inflation, a moment when the universe's expansion wasn't perfectly uniform, leaving behind a faint directional bias like a cosmic brushstroke. The octopole's defiance of randomness isn't just a statistical quirk. It's a breadcrumb trail leading us toward deeper questions about the universe's infancy. Whether it's primordial magnetism, observational illusions, or something even stranger, this alignment challenges us to rethink how much we truly understand about the cosmos's first moments. And until we unravel it, the CMB's 8-lobed whisper remains one of its most beguiling riddles. The cosmic microwave background isn't just a snapshot of the early universe, it's a forensic record of the countless collisions and interactions that shaped it. And when we zoom in on its smallest fluctuations, we stumble upon something called silk damping, a peculiar smoothing effect that shouldn't be as pronounced as it is. Picture the infant universe as a dense, seething plasma, where photons and electrons are locked in a violent dance, constantly scattering off one another. As the cosmos expanded, this chaos left behind a subtle fingerprint. Smaller-scale temperature variations got smeared out, like ripples in a pond fading as they spread. This damping effect, named after physicist Joseph Silk, is expected, but the degree to which it appears in the CMB has cosmologists scratching their heads. Here's the rub. Silk damping's observed strength clashes with predictions from some of our most trusted inflation models. These models suggest that quantum fluctuations during inflation should have seeded sharper, more pronounced small-scale structures in the CMB. Instead, the damping tail, the drop-off in fluctuation strength at finer scales, is smoother than expected, as if something blunted those primordial wrinkles. It's like expecting a jagged mountain range and finding gently rolling hills. So what could have ironed out these cosmic creases? One tantalizing possibility involves actions, hypothetical particles so light and weakly interacting they've been dubbed fuzzy dark matter. Unlike the sluggish cold dark matter we usually consider, actions would behave more like a quantum fog, their wave-like nature smearing out small-scale structures. Think of it like trying to paint fine details with a brush that's slightly too thick. The result is softer, less defined. If actions or similar ultra-light particles were abundant in the early universe, their peculiar quantum interference might have suppressed the growth of tiny density fluctuations, leaving the CMB's damping tail smoother than inflation alone would predict. But not everyone's sold on the action fix. Skeptics argue that tweaking inflation's parameters, like the energy scale at which it occurred, could achieve the same damping effect without invoking new particles. Others point to the possibility of incomplete modeling. Maybe the way photons and electrons scattered during recombination wasn't as uniform as we assume, leaving gaps in our calculations. There's even a wild-card idea that primordial magnetic fields threading through the early plasma could have altered the damping pattern by jostling charged particles in unexpected ways. The Silk damping puzzle isn't just a technical hiccup. It's a tug-of-war between the very large and the very small. If actions are the answer, they wouldn't just solve this cosmic riddle. They'd open a window into a hidden sector of particle physics, one where dark matter isn't a single monolithic entity, but a spectrum of ghostly particles with bizarre quantum properties. On the other hand, if inflation models need revising, it could mean our understanding of the universe's explosive birth is more incomplete than we thought. For now, the CMB's smoothed edges remain a silent challenge, a whisper from the early universe that defies easy explanation. Whether it's actions, tweaked inflation, or something even stranger, one thing's clear: the cosmos is still holding secrets, and the clues are written in the faintest brushstrokes of its oldest light. Gravity doesn't just bend the paths of planets and stars, it warps light itself, twisting the very fabric of the cosmos into a funhouse mirror. And when it comes to the cosmic microwave background, this phenomenon, known as gravitational lensing, leaves behind some of the most tantalizing and baffling fingerprints. As CMB photons travel across the universe, their journey is subtly altered by the gravitational pull of everything in their path. Galaxies, dark matter halos, even vast cosmic voids. These distortions should be faint, predictable, a gentle ripple in the ancient light's trajectory. But when scientists mapped the CMB's lensing patterns, they found something peculiar, some regions where the warping is stronger than it should be, as if invisible hands were tugging at spacetime with unseen strength. Think of it like looking at a street lamp through a frosted window. The glass distorts the light, but in a way that's smooth and uniform. Now imagine patches where the frost suddenly thickens, bending the light more sharply in certain spots. That's the essence of the lensing anomaly, an unexpected unevenness in how the CMB's light gets twisted. The most puzzling part: these excess distortions align with areas where galaxy clusters are scarce, meaning the extra warping can't be explained by visible matter alone. It's as if something hidden, something beyond our current maps of mass, is amplifying gravity's grip in these regions. One radical explanation points to modified gravity. Einstein's theory of general relativity has been the gold standard for a century, but what if it's incomplete? Alternative theories like modified Newtonian dynamics propose that gravity behaves differently at cosmic scales, strengthening where conventional physics says it should weaken. In this scenario, the CMB's excess lensing could be a sign that gravity doesn't play by Einstein's rules in the universe's emptiest quarters. Imagine a game of cosmic pinball where the flippers suddenly get stronger in certain zones. The ball would veer unpredictably, just like those lensed photons. But there's a catch. If modified gravity is at work, why doesn't it leave clearer fingerprints elsewhere? Galaxy rotations and cluster dynamics mostly align with general relativity's predictions, leaving to fill gaps rather than rewrite the rules. Some theorists argue that the answer lies in dark matter's quirks, not its absence. Perhaps dark matter isn't as smoothly distributed as we think, clumping in invisible filaments or exotic forms that intensify lensing in unexpected ways. Others suggest that primordial black holes, scattered like hidden anchors in the cosmic web, could be warping light more than models account for. Then there's the skeptic's take: maybe we're misreading the data. Lensing measurements rely on untangling the CMB's subtle fluctuations, a process vulnerable to noise from interstellar dust or biases in statistical models. Even tiny errors could exaggerate the apparent anomalies. Yet as telescopes like the Atacama Cosmology Telescope refine their observations, the excess lensing stubbornly persists, refusing to fade into statistical noise. The gravitational lens twist isn't just a technical hiccup, it's a tug of war between the known and the unknown. Whether it's evidence of new physics, dark matter's hidden structures, or something even stranger, one thing's clear: the universe's funhouse mirrors are showing us reflections we don't yet understand. And until we solve the riddle, every distorted photon is a reminder that gravity, the force we thought we knew, might still have secrets to spill. If the Hubble tension wasn't puzzling enough, another cosmic rift is deepening the mystery, one that ties the expansion rate of the universe directly to how galaxies clump together. This is the H0 sigma 8 tension, a mouthful of a problem that exposes a glaring mismatch between two fundamental cosmological parameters: the Hubble constant H0, which measures how fast the universe is expanding today, and sigma 8, which quantifies how tightly matter has clustered into galaxies and filaments over cosmic history. According to our best models, these values should dance in lockstep, their relationship choreographed by dark energy and dark matter's gravitational tug. But the universe, it seems, has other plans. The tension arises when we compare predictions from the cosmic microwave background with observations of the large-scale structure of the universe. The CMB's pristine snapshot of the early cosmos lets us extrapolate how sigma 8 should evolve as dark energy accelerates expansion and dark matter sculpts the cosmic web. Yet when astronomers map galaxy distributions today using surveys like the Dark Energy Survey or the Sloan Digital Sky Survey, they find fewer galaxy clusters and sparser filaments than the CMB's predictions suggest. It's as if the universe's scaffolding grew fainter, its threads looser over billions of years. Here's where things get especially strange. This sigma 8 discrepancy appears to be entangled with the Hubble tension. A universe expanding faster than expected, as local H0 measurements imply, would naturally have less time for matter to clump, potentially explaining the lower sigma 8 values. But the CMB-derived Hubble constant, the one that does align with sigma 8, clocks the expansion slower. It's a cosmic catch-22. The numbers refuse to reconcile, forcing us to question whether dark energy's influence has changed over time or if gravity itself behaves differently on epoch-spanning scales. One provocative explanation is that dark energy isn't the static force we've assumed. Lambda, the cosmological constant in Einstein's equations, might not be so constant after all. If dark energy's strength waxed or waned across cosmic history, it could simultaneously explain both tensions. An early surge in dark energy might have suppressed galaxy clustering, fixing sigma 8, while a later weakening could slow today's observed expansion, resolving H0. Imagine a car's accelerator pedal that pulses unpredictably, sometimes pressing harder, sometimes easing up, leaving us puzzled by its inconsistent speed. But tweaking dark energy isn't the only option. Some theorists argue the answer lies in the dark sector's complexity. What if dark matter interacts with itself or with dark energy in ways we haven't accounted for? Self-interacting dark matter, for instance, could scatter like billiard balls, smoothing out cosmic structures and lowering sigma 8 without altering the expansion rate directly. Alternatively, if dark matter decays over time, its dwindling gravitational grip might mimic the effects of a shifting dark energy. Then there's the radical fringe. Maybe general relativity needs an update. Modified gravity theories, like those that tweak Einstein's equations on cosmic scales, could in principle recalibrate the relationship between expansion and clustering. But these proposals often struggle to match all observational constraints without introducing new paradoxes. The H0 sigma 8 tension isn't just a technical disagreement. It's a signpost pointing to gaps in our understanding of the universe's most dominant yet enigmatic components. Whether it's dynamic dark energy, exotic dark matter, or revised gravity, solving this puzzle won't just reconcile two numbers. It could reveal a cosmos far more dynamic and interconnected than we've ever imagined, where the forces shaping galaxies are inextricably tied to the fate of spacetime itself. Until then, the mismatch lingers, a silent challenge written in the stars and the spaces between them. What if the cosmic microwave background isn't just a relic of our universe's birth but a graveyard of other, long-dead universes? Picture this. The vast expanse of space isn't a lonely, solitary bubble but one foam in an endless cosmic ocean, where other universe domains constantly collide, merge, and vanish. This is the wild frontier of eternal inflation theory, and buried within the CMB's subtle temperature fluctuations might be bruises from these ancient cosmic crashes, ghostly imprints of universes that once touched ours. Stephen Feeney's controversial work ignited this debate when his team analyzed data from the Wilkinson microwave anisotropy probe, hunting for telltale circular patterns in the CMB's temperature variations. These so-called bubbles aren't just random noise, they're concentric rings, like ripples frozen in a pond where the temperature shifts abruptly at the edges. Feeney argued these could be scars from universe-scale collisions, moments when another expanding spacetime domain slammed into ours during its earliest, most violent expansion. Imagine two soap bubbles in a sink, brushing against each other before recoiling, except these bubbles are entire universes, and their collision leaves a faint thermal residue in the CMB's glow. Critics, though, aren't sold. The statistical significance of these bubbles is razor-thin, and alternative explanations like instrumental noise or foreground galactic dust could mimic the same patterns. Even Feeney himself acknowledged the findings were tentative, more provocative than conclusive. Yet the idea refuses to die because it taps into a deeper question. If eternal inflation is real, shouldn't there be evidence of other universes out there? Inflation theory suggests our cosmos is just one pocket in an eternally inflating multiverse, where new universes sprout endlessly like buds on a branching tree. If true, collisions between neighboring pockets wouldn't just be possible, they'd be inevitable. The real challenge is distinguishing these cosmic bruises from mundane astrophysical effects. One clue lies in the bubble's polarization signatures. A true universe collision would twist the CMB's polarized light in specific ways, creating swirling B-mode patterns distinct from those caused by gravitational waves or dust. Future telescopes like the Simons Observatory or CMB S4 could settle the debate with their unprecedented sensitivity to these subtle fingerprints. If these bubbles are real, the implications are staggering. Not only would they confirm the existence of other universes, they'd offer a glimpse into the physics that govern them. The temperature gradients at the edges could reveal the energy density of the colliding domain, hinting at its fundamental constants. Did that other universe have more dark energy, different particle physics, a faster speed of light? Each collision signature would be a Rosetta Stone for decoding the rules of realities beyond our own. For now, the eternal inflation echo remains a tantalizing maybe, a whisper in the static that could rewrite our place in the multiverse or fade into the noise of cosmic uncertainty. But whether these bubbles are cosmic ghosts or mere mirages, they remind us that the CMB isn't just a snapshot of our past. It might be a mosaic of everything that ever was or could have been, written in the faintest etchings of microwaves. One of the most haunting absences in the cosmic microwave background isn't what we see, it's what we don't. Scattered across the universe, vast structures like galaxies and superclusters trace the distribution of matter, the building blocks of everything we know. But matter has a mirror image, antimatter, its equal yet opposite counterpart, which should have been created in equal amounts during the Big Bang. Yet when we scan the CMB for signs of antimatter-dominated regions, cosmic territories where antiprotons and positrons reign, we find nothing. No shadows, no borders, no fiery annihilation fronts where matter and antimatter meet. The universe appears almost surgically cleansed of its antimatter half, and no one knows why. This isn't just a curiosity, it's a violation of one of physics' deepest symmetries. According to everything we understand about particle interactions, the early universe should have produced matter and antimatter in perfect balance. Yet here we are, in a cosmos made entirely of matter, with antimatter relegated to rare, fleeting appearances in particle colliders or cosmic rays. The CMB amplifies the mystery. If baryogenesis, the process that tipped the scales toward matter, happened unevenly, patches of antimatter could have survived, floating like islands in a matter-dominated sea. These domains would leave glaring imprints in the CMB, temperature asymmetries, polarization twists, even sharp edges where annihilation gamma rays would blaze. But the maps are blank. It's as if the universe took one look at antimatter and hit delete. The alpha experiment at CERN adds another layer to the puzzle. There, physicists trap and study antihydrogen, the antimatter counterpart of hydrogen, with breathtaking precision. Their measurements confirm that antimatter obeys the same laws of physics as matter, its spectral lines, its response to gravity, even the way it absorbs and emits light. If antimatter behaves so identically, why didn't it stick around? The CMB's silence suggests the imbalance wasn't just a minor statistical fluke, but a fundamental rewriting of the rules, something that acted universally and decisively. The leading theory, called leptogenesis, proposes that ghostly neutrinos, particles that barely interact with anything, might hold the key. In the earliest moments, these neutrinos could have decayed asymmetrically, producing slightly more matter than antimatter. But the CMB throws cold water on even this elegant idea. If leptogenesis left behind antimatter pockets, they'd need to be vanishingly small or impossibly distant to evade detection. Alternatively, some unknown force might have actively suppressed antimatter, like a cosmic filter scrubbing it from existence. The absence of antimatter in the CMB isn't just a missing piece, it's a gaping hole in our understanding of the universe's first seconds. Whether it points to undiscovered particles, hidden forces, or a flaw in our theories, one thing's clear: the cosmos is playing favorites and we're still struggling to read the rules. If spacetime were a vast ocean, the cosmic microwave background photons would be ancient travelers crossing its surface, each carrying memories not just of where it's been, but of the very fabric it moved through. And if quantum mechanics holds true, that fabric isn't smooth. At scales a trillion times smaller than an atom, space-time itself is theorized to churn with turbulence called quantum foam, a seething froth where tiny wormholes flicker in and out of existence, and the concepts of here and now lose all meaning. The mind-bending question is, could photons from the CMB, after journeying for over 13 billion years, bear subtle scars from this subatomic chaos? The idea hinges on a phenomenon called quantum decoherence. Imagine a photon traveling through this frothy spacetime. Each time it interacts with a fleeting bubble or ripple in the quantum foam, its path would jitter ever so slightly, not enough to change its direction outright, but enough to smear its wavefront like a runner stumbling on unseen pebbles. Over cosmic distances, these infinitesimal deviations could accumulate, leaving a telltale blur in the CMB's polarization patterns. It's as if the universe's oldest light carries encrypted notes about the structure of reality at its smallest scales, notes we're only now learning to read. The challenge is isolating this signal from the noise. Current telescopes like Planck lack the precision to spot these Planck-scale fingerprints, but next-generation observatories like CMB-S4 or the proposed PICO satellite might change that. These instruments will map the CMB's polarization with unprecedented fidelity, searching for a specific statistical anomaly, an excess of V-mode polarization, a twisted pattern that conventional physics can't explain. If found, it could be the smoking gun of quantum foam, evidence that spacetime isn't just warped by massive objects like stars, but is inherently turbulent at levels we've never probed. Skeptics, though, argue that such a signal could easily be mimicked by cosmic dust or systematic errors in data processing. Even the faintest interference from interstellar magnetic fields could mimic the blurring effect of quantum foam. To rule out false positives, researchers are developing innovative cross-correlation techniques, comparing CMB data with ultra-deep galaxy surveys to map where contamination might lurk. It's a cosmic game of spot the difference, where the stakes are nothing less than confirming whether spacetime itself has texture. The implications are staggering. If quantum foam's signature is real, it wouldn't just validate theories like loop quantum gravity, it would open a direct window into the Planck epoch, the universe's first fraction of a second when gravity and quantum forces were indistinguishable. We might even glimpse signatures of a pre-Big Bang geometry, hints that our cosmos inherited its quantum structure from something older. Or the signal could vanish, forcing us to reconsider whether spacetime is smooth after all, a revelation equally profound. For now, the quantum foam's whisper remains buried in the CMB static, a riddle wrapped in microwaves. But with every advance in telescope sensitivity, we edge closer to answering a question that bridges the cosmic and the quantum. Is the fabric of reality grainy, and if so, what secrets do those grains hold? What if the universe's deepest mysteries aren't just unsolved, they're intentional? Among the most provocative theories bubbling up from the cosmic microwave background's anomalies is the idea that these glitches aren't cosmic accidents but artifacts of a deeper architecture. Enter the simulation hypothesis, the notion that our reality might be an elaborate construct, a digital universe running on unfathomable hardware, with the CMB's quirks as its telltale pixels or even error-correcting code. It's a radical take, one that blurs the line between science and science fiction, but for some physicists, it's a framework worth taking seriously. Silas Bean, a nuclear physicist at the University of Washington, added fuel to this speculative fire with a startling paper. His team modeled how a simulated universe might behave if built on a lattice, a grid-like structure of discrete points like pixels on a screen or atoms in a crystal. The implications were eerie. In such a universe, fundamental laws would break down at extremely high energies or tiny scales, revealing the underlying resolution of the simulation. Bean suggested that if our cosmos were programmed, these limits might appear in cosmic rays, but others argue the CMB could harbor even subtler fingerprints, Imagine finding jagged edges in a supposedly smooth curve, or mathematical redundancies in temperature fluctuations that resemble the error correction protocols in computer code. These wouldn't just be oddities, they'd be smoking guns of a universe with an instruction set. The most tantalizing lead comes from the CMB's so-called pixelation. Some researchers claim the temperature fluctuations aren't entirely random but align in ways reminiscent of a low-resolution image blown up too large. In a simulated reality, the universe's textures might be rendered with finite precision, leaving behind faint grid-like patterns when stretched across billions of light years. Others point to anomalies like the axis of evil or the cold spot as potential buffer overflows, glitches where the simulation's calculations strained against its own limits. Even the CMB's near-perfect blackbody spectrum, often hailed as evidence of cosmic naturalness, could be reinterpreted as the signature of an optimized rendering engine, a universe running on efficient, minimalist code. Yet the simulation hypothesis isn't without its paradoxes. If the universe is a program, who or what wrote it, and why embed clues in the CMB at all? Some theorists argue that advanced civilizations might leave Easter eggs in their creations, while others counter that any simulators capable of building such a reality would have patched these bugs long ago. Then there's the observational hurdle, distinguishing true simulation artifacts from mundane astrophysics. The cold spot could be a supervoid, the axis of evil might be galactic dust. Without a way to test the simulation claim directly, it risks becoming a cosmic version of solipsism, an idea impossible to disprove but equally hard to embrace. Still, the hypothesis forces us to confront the unnerving possibility that the CMB isn't just a relic of the Big Bang but a debug log for reality itself. Whether it's a flawed metaphor or a paradigm-shifting insight, one thing's clear: the deeper we probe the universe's oldest light, the more it seems to reflect our own hunger for meaning, in pixels, patterns, or something stranger we've yet to name. From the eerie uniformity of the cosmic microwave background to its inexplicable cold spot, from the axis of evil's unsettling alignment to the missing supervoid's gravitational ghost, these 25 mysteries aren't just cosmic curiosities, they're proof that the CMB is more than a relic. It's cosmology's Rosetta Stone, a cipher written in microwaves that holds the keys to everything from dark matter's secrets to the universe's very shape. Each anomaly is a breadcrumb leading us deeper into questions we're only beginning to ask. Why does the CMB's large-scale structure refuse to match predictions? Could its lensing distortions hint at unseen forces? And what if its perfect blackbody spectrum isn't perfect after all, hiding whispers of quantum foam or even other universes? The deeper we look, the clearer it becomes. This ancient light isn't just a snapshot of the past. It's a living puzzle, daring us to rethink reality itself. Upcoming missions like CMB S4, Light Bird, and the Simons Observatory are poised to turn speculation into revelation. With sensitivity 100 times greater than Planck's, these telescopes will scan the CMB's polarization for traces of primordial gravitational waves, hunt for the fingerprints of cosmic strings, and test whether the cold spot truly defies physics. They might even settle the Hubble tension once and for all, or deepen it into a full-blown revolution. The stakes couldn't be higher. Every new datum could rewrite our cosmic story, proving the universe is stranger, richer, and more interconnected than we've ever dreamed. So which mystery grabs you? Is it the phantom tug of the dark flow, hinting at realms beyond our horizon? The lithium deficit that refuses to fit the Big Bang's ledger? Or the eerie quantum echoes that might betray spacetime's pixelated core? The beauty of these enigmas is that they're not just for scientists, they're for anyone who's ever looked up at the night sky and wondered what's out there. Because the CMB isn't just a scientist's tool, it's humanity's oldest heirloom, a message bottled in the dawn of time, waiting for us to decode it and the next chapter. That's yours to follow, so keep watching the cosmos. The best clues are still coming into focus.